Now let me talk about one of the tools, statistics that Bayesians use for model comparisons, Bayes factor. Bayes factor. And before I get into details about Bayes factor, let me invoke Bayes rule Bayes theorem again. So here we have this Bayes theorem, right? The probability of posterior probability of the model given the data is equal to the ratio, okay? And in the numerator of the ratio, we have the probability of, or the likelihood of observing data given the model multiplied by the prior probability of the model just by in the denominator the probability of data. And if we have two models we can take a ratio of these two posterior, it's called posterior odds, right? And then plugging all these terms on the right-hand side. Now, the probability of observing data here, this term drops out. And after simple rearrangement, we will get two terms or two ratios on the right. First is the likelihood ratio, and then is the prior ratio, prior odds, right? And the likelihood ratio is the Bayes factor, and a target, quantity, a quantity of interest for us to compute. And the Bayes factor is, we can also understand Bayes factor as ratio of the posterior odds, okay, of M1, right? So this is the posterior odds of M1, right, over M2 to its prior odds, right? Again, M1 over M2 if we move this term to the right, right? Regardless of the value of the prior. And based on publication by Cass and Raftery in 1995, and Jeffrey in 1961, we have this table of guidelines for Bayes factor in adjudicating, in this case, between two models, right? If the Bayes factor is from 1 to 3, then evidence is now worth more than a bare mention. Basically here is the Bayes factor of model 1 versus 0, right? Or hypothesis 1 versus hypothesis now. Okay? If the Bayes factor is equal to 3 to 20, then there's a positive evidence in favor of the model in the numerator of the Bayes factor, if you recall. If it is equal to 20 to 150, then there is a strong evidence. If the Bayes factor is greater than 150, then there's a very strong evidence. Sometimes we can also take a natural log of the Bayes factor and multiply by 2, then it's going to scale down the Bayes factor. But either way, we can get, the equivalence of raw Bayes factor on the log scale multiplied by 2, and we're going to lead to the same conclusion, okay? Next is about some computational details for Bayes factor. So we begin with Bayes theorem again, right? The same formula we discussed in the previous slide, which is going to lead to, this equation, right? On the left-hand side, we have this posterior odds, and on the right-hand side, we have this product of likelihood ratio and prior odds. We're going to compute, our goal is to compute these two terms, right? The probability or the likelihood of data given the model, or basically the likelihood. So what is that equal to? A generic quantity or likelihood. That is equal to integral of, the probability of or the likelihood of having the data, empirical data, given data K and model K, okay, multiplied by this prior, that is, the probability density of parameters given model MK, okay? So this pi, the probability of theta K given model K is called prior density. And this term, okay, also this term, and that is likelihood of data or probability of data given theta K and model K, okay, is the probability of the data, likelihood of data, conditional on theta K and MK. Again, let me bring you back to our target, that is the probability, or the marginal probability of data, okay, of data, by integrating the joint density of data and theta K given data over theta K. So it's going to integrate out theta K so that we're left with model as this only conditioning factor, only conditioning factor. Well, this marginal probability, is our target, right? Because we're going to calculate the likelihood ratio, and so we need to compute this marginal probability in the numerator for model 1, and the marginal probability, in the denominator for model 2, and it is only valid, okay, while being computed with proper priors. Okay, so if we're given proper prior, since we need to, we need to integrate out, right? Proper prior, okay, proper prior. Not improper priors. So people say, what is improper prior? Well, improper priors refer to priors that are now integrable, or its cumulative density function is greater than 1. It's just not going to be integrated to 1, right? That's kind of major condition for a probability density to be called a proper prior. Okay? More computational details, and according to Cass and Adrian Raftery, they figure out that to figure out this marginal probability, or marginal likelihood, right? And they denote it as I here. Okay, we can use what is called Laplace method of approximation. The thing is how to approximate this I. Well, let's begin with log of theta. Okay, log of theta, okay? Tilde. Right? And let's say log of theta for this L tilde. So this is L, okay, L, okay? Tilde is equal to the log of these two terms, product of these two terms. That is the probability of observing data given parameter and model setup multiplied by prior density, prior given the model. Okay, and let's say we have this theta tilde, after MCMC simulation, we can derive the posterior. And theta tilde is this posterior mode. Okay, posterior mode. And next, what we're going to do, we're going to expand this log of the product, that is L tilde, right? This L tilde. Okay, about theta tilde. Okay, and we can do, for example, Taylor, series expansion. We can expand this function, right? L tilde about theta tilde. And then what we're going to do, we take exponential of that, because we take a log. Then we take exponential of that. It's going to yield an approximation of this one, right? Because L tilde takes a log of these two terms, right? Take a log of these two terms. Now, first we need to do, first we did is, we try to approximate now this term, okay? By expanding, log of tilde about theta tilde. Then we take exponential function, okay? Because we have a log here. Then we're going to get back to approximation of this term, okay? In that case, we're going to have a form of a normal density with a mean of theta tilde and covariance matrix. This term basically, inverse of Hessian matrix. Well, what we're going to do next? Well, since there's integral there, we're going to integrate out, okay, this approximation. Then it's going to yield I hat, which is equal to this, pretty ugly looking or very beautiful looking long term. And in this case, this is pi, and we have d. What is d here? D is the dimension of theta. And again, we have covariance matrix, estimated at theta tilde, right here, which is the inverse of the Hessian matrix. And the square root of that, then we're going to have, product of these two terms, which has been estimated previously. And note that theta tilde is this posterior mode.